Welcome and thank you for joining. In this lesson, we'll analyze finite differences and discover the connection between them and equations of polynomial functions. Now, remember that finite differences are changes in the y values as x values increase by equal intervals of 1 unit. Now, finite differences are used to determine the equation of a polynomial function when only a table of values is given, so we can discover the equation by using a table of values. In this lesson, we'll investigate the polynomial functions of degrees 1 through 3 and see how finite differences can be helpful at determining the degree of a polynomial function. And we're going to learn how to identify patterns in a table of values and ultimately develop an equation of a polynomial function from finite differences. Now, to determine finite differences, we start with their first differences, which are found by subtracting consecutive y values. Now, second differences are found by subtracting the first differences values, so they're the differences of the first. And third differences are the differences of the second differences. And we can continue this process until the differences become constant, or we should say when the differences stop changing or finish their change. And this is, by the way, where the word finite is rooted in. So when the differences finish changing, then we're going to stop there and we're going to be able to determine the degree of the polynomial function just based on that. So finish finite, remember that. Now, how do we determine the degree of a polynomial? Well, if the first differences are constant, then we're going to say it's a first degree or a linear polynomial function. We have explored this in grade 9 as well, if you remember. If the second differences are constant, it's going to be a second degree or a quadratic polynomial. If third differences are constant, it's a third degree over cubic polynomial. And we can continue this process until the differences stop changing or finish their change until the nth degree. If nth degree polynomial, then we're going to expect the nth differences to be constant. So the key idea here is that the first constant finite differences will give us information about the degree of the polynomial function. So if the nth differences are constant, it will be nth degree. And understandably, as the degree of a polynomial function increases, then the complexity of the pattern in the increase of y values will change, and that's why we have to go for higher differences. We're going to start off with linear functions. So in the form y equals mx plus b. So I have selected values of x that are increasing by 1. They're consecutive x values. You can also choose values such as 100, 101, 102. It doesn't really matter. But it is a lot easier to choose smaller numbers. So I selected some positives, some negatives, and 0. Now, in this case, we are given the equation because we want to explore and discover how the differences of the specific equation are connected to the equation. So it's an investigation, that's why. So we're going to start off with the y values here. So when x equals 2, the y value will be m times negative 2 plus b, or simply negative 2m plus b. Next we have x equals 1, so the y value will be m times negative 1 plus b, or negative m plus b. When x equals 0, m times 0 plus b will be equal to simply b. When x equals 1, m times 1 plus b, or simply m plus b. And when x equals 2, we have m times 2 plus b, or 2m plus b. So as you can see here, we have obtained the following y values, which I will be highlighting so we can conveniently use them to find the first differences. Now, the first differences, as we mentioned, are found by subtracting a y value from the second, or from this y value, we subtract its previous. So you can say it in either way. So negative m plus b, subtract, we have negative 2m plus b. So let's make the subtraction here, right? So it stands out. And I want to bring your attention in here to the fact that whenever you subtract more than one term, you got to keep that in brackets to remind yourself that each term is being subtracted. So minus negative 2m is positive 2m, minus positive b is minus b. So b and negative b will simplify to 0, or will add to 0. Negative m plus 2m will give m. Next we have the differences between b and negative m plus b. So similarly, we have b minus negative b plus m, and then minus positive b is minus b. So again, we're simplifying the constant, or the constants will add to 0, and we get m again. And you're probably not surprised, we've seen this in grade 9 as well, but it's good to refresh our memory. And next, we're going to look at, let me just bring this a little bit higher so they're kind of aligned. We have m plus b, and then subtract b. We are subtracting only one term, no brackets are needed. B is simplifying again, so we're getting the value m. And next we're going to have the value of 2m plus b, and we're subtracting m plus b. So we're subtracting two terms. We got to keep it in brackets. And 2m plus b minus m minus b will give 2m minus m equal to m, so the value will be m. So as you can see, delta 1 is constant. And I'm going to stop actually for a second, just so in case anyone needs this explanation. So when we talk about differences, so the symbol we use for second differences or first differences in general, is this little triangle, which actually is the letter D in Greek, and letter D in Greek is read as delta, and that's the word that we're going to use as well, delta 1. So we use this to signify the first letter of the word difference in English. So we're going to say that in our case, the first differences are constant, so this will be our conclusion number 1. So delta 1 is constant. That tells us that this will be a first degree polynomial function. And not only this, but we've also discovered that delta 1 is equal to the value of m. And we're going to use this fact to determine the equation of an unknown function from a table of values by using the first differences. So whatever first differences we get in the table of values, if that is constant, that makes for the value of m, or the slope, or the leading coefficient. So delta 1 is equal to the leading coefficient in linear functions, obviously. And the last thing that we need to actually focus on is this little coefficient b here. So the coefficient b, if you look at the table of values, is found as the y value, which is b, when x equals 0. So that will always give us the coefficient b. So for the coefficient b, we're going to say that it would be equal to the y value at x equals 0. So with this in mind, we're going to start with our first example and try to determine the equation of the function that is hiding behind this table of values. First, I want to check that the x values are changing by 1 and only 1 unit. And then I'm going to start with finding the differences between the y values. So let's see, let's try to make this a little bit fancy. And we have first 8 minus 14, that's negative 6. 2 minus 8, negative 6. Negative 4 minus 2, negative 6. Negative 10 minus negative 4, that's negative 10 plus 4, again negative 6. Negative 16 minus negative 10 is negative 16 plus 10, negative 6. So we're going to say that delta 1 is constant. Therefore, this is going to be a first degree polynomial function. And therefore, again, we're going to say that the equation that we should be looking for should be in the form y equals mx plus b. So in this equation, it is our job to find the values of m, oh that was too thick, so m and the value of b. For the value of m, we're going to say that that would be equal to delta 1. And for the value of b, we're going to say is y at x equals 0. So looking at delta 1, we see that that equals negative 6. So therefore, the slope is negative 6. And looking at the value of y at x equals 0, it seems that is equal to 2. So the value of b would be 2. So the equation of this relation represented by the table of values we're given here would be negative 6x plus 2. This would be the slope y-intercept form. And if the equation is asked in standard form, then you can just take the terms to the other side of the equation, and voila, this will be another form of this equation. Now there is another example here, very similar to what we just did, different numbers, and you can try this on your own. Stop the video. I will continue explaining this just in case you want to follow along. So we're going to start off by checking that the x values are changing by 1 unit. So it seems that they are increased by 1, so we're good to go. So we're going to start off with the differences. 5.5 subtract 6, that's negative 0.5. We have 5 minus 5.5, that's another negative 0.5. We have 4.5 subtract 5, that's another negative 0.5. 4 minus 4.5, so you can see that the pattern is consistent and we are getting the same constant difference of negative 0.5, which means that this relation is linear. And delta 1 is going to be negative 0.5. It's constant, which will make the relation linear or first degree. And that means that the equation that we should be looking for would be in the form y equals mx plus b. So for the slope, we look at delta 1 because slope is equal to delta 1, in our case negative 0.5. And for the y-intercept, we're going to look at x equals 0. That would give us the value of the y-intercept, which in our case is equal to 5. So we're going to say that with a y-intercept of 5 and a slope of negative 0.5, we're ready to write the equation. And the equation will be in the form negative 0.5x plus 5. Don't forget this x, people tend to, because that won't give you the correct equation, obviously. It will make a constant right side, which is incorrect. Now, another way of writing this same equation is negative 1 over 2x plus 5. And if you want to write this in standard form, we got to get rid of that denominator. We do so by multiplying every term by number 2. And that will simplify the denominator, but it will change the other terms, obviously. And the standard form would be x plus 2y minus 10 equals 0. And this would be the answer to the question number 1b. Now we'll continue in the next video with the patterns that we discover between finite differences and the second degree polynomial functions. Until then, bye for now, and thank you for learning with me.